Welcome to another lecture on design and analysis of algorithms. Our topic for today is matrix chain multiplication. Let me begin with an informal statement of the problem that we have. Okay. So, our problem is something like this. We are given n matrices, let us call them m1, m2 all the way till m sub n, and we would like to multiply them and form this product. So, this is a usual matrix product. We would like to do this as fast as possible. Here are some of the issues involved in doing this. So, the first issue is what algorithm should we use when we just multiply two matrices together, because we are going to be using this algorithm repeatedly. That is how we are going to solve this problem today. The second issue is, since matrix multiplication is associative, how do we parenthesize this product? Because that will it will be clear soon that that will also affect the time required to do the entire to form the entire product. So, let us look at the first issue. So, let us say we want to compute C equal to A times B, where A is a P by Q matrix, B is a Q by R matrix, A and B are given to us, and C is a P by R matrix which is to be computed. The simplest algorithm for doing this is to use the definition of matrix multiplication. Matrix multiplication is defined as Cij is equal to summation over k going from 1 to q of ai k times pkj. Computing a single term such as Cij will require O of q time. C has Pr elements overall. C is a P by R matrix, so it has Pr elements. So, the total time will be O of PQR. Now, turns out that there are faster algorithms possible, but we are going to stick to this algorithm for simplicity. So, we will assume for the rest of the lecture that if I want to just multiply two matrices together, my time is going to be O of PQR, or to make it even simpler, I am going to just say PQR is the time required for multiplication of two matrices, a P by Q matrix and a Q by R matrix. The second issue concerns associativity. Let me explain this with a specific example involving only three matrices. So, say n is equal to 3 over here. Now, we need to compute the product m1 times m2 times m3. There are two ways to do this. One possibility is to multiply m2 and m3 first and then multiply that with m1, or multiply m1 and m2 first and then multiply that with m3. Let us take a specific example. Okay. So, let us assume that M1 is a 3 by 2 matrix, okay. M2 is a 2 by 4 matrix, and M3 is a 4 by 1 matrix. So, now if we want to multiply it according to this manner, okay, then here is what will happen. So, we will first compute some matrix M4, which is M2 times M3. So, M2 was a 2 by 4 matrix and M3 was a 4 by 1 matrix. So, the product will be, following our formula PQR, it will be 2 times 4 times 1, or it will be 8. Okay. Now, given M4, our final answer can be computed just by multiplying M1 with it. M1 is a 3 by 2 matrix, okay, and M4 we calculated was a 2 by 1 matrix. So, this will require time 3 by 2 by 1 or 6. So, this will require 6 matrix multiplication, 6 scalar multiplications, this will require 8 scalar multiplications. Then the total number of multiplications required will be 14. Another possibility which I have indicated over here is to first form M1 times M2. So, we compute M5 equals M1 times M2. Remember that M1 was a 3 by 2 matrix and M2 was a 2 by 4 matrix. So, the total time over here to calculate M5 is equal to 24. The answer now can be obtained by multiplying this M5, which is just this, which we calculated, by M3. Now, M5, the product was 3 by 4. So, its P and Q are 3 and 4. M3 is 4 by 1. So, Q by R is 4 and 1. So, this product requires time 3 times 4 times 1 or 12. The total time for this way of doing things is therefore 24 plus 12, which is equal to 36. So, clearly this first way is better. The problem now is that if we can take our product and we can parenthesize it in this way, or we can parenthesize it in this way. We could speak of parenthesizations, but I would like to point out that these parenthesizations can also be thought of as rooted trees. So, let me explain that. So, here are our matrices to be multiplied, M1, M2, M3. So, if I want to first form the product M2 times M3, let me represent it in our usual fashion by drawing a vertex over here, and this vertex represents their product. The next thing I do is I take the product of these two, and this is my final answer. So, this corresponds to the parenthesization M1 times M2 times M3. Alternatively, I could also have done something like this. So, I could take product of M1 and M2 first. So, this is the first way of doing things. This is what I do first, and then I take the product of those. So, the parenthesization corresponding to this is M1 times M2 whole times M3. Okay, so, this is this way of doing things which we had indicated earlier. In this particular example, we found that this way was superior, but of course, with other choices of the matrix dimensions, other ways could be superior. This could be superior. We want to multiply n matrices and not just 3. So, let us just do one more example. What if we have 4 matrices? So, in this case, we have matrices M1, M2, M3, M4. So, the parenthesizations here will correspond to a tree with 4 leaves. So, one possible parenthesization which I might indicate is something like this. So, say for example, I could compute say the product of M2 and M3 first, okay. Then maybe I compute product of M3 and M4 next, and then finally I compute this. Okay. So, this is the tree. Of course, there are many such trees possible, and in fact, in this case let me just write down all those. Okay. So, say for example, here is another tree. Okay. So, here is another tree in which we first multiply M3, M4, then multiply that with M2 and then with M1, but that is not only one, here is another. Okay. And then we also have things like and also so in this case it turns out that there are 5 trees in which M1, M2, M3, M4 can be the leaves, and therefore 5 ways of parenthesizing this product. As you saw, to go from 3 to 4, we went from 2 to 5. If you keep doing this, you will see that the number of trees grows very fast. In fact, you should be able to prove that it grows exponentially. So, the point is that we want to pick a tree from one of these possible trees, and we want to pick the one which minimizes the total time taken. So, we are now ready to give a formal statement of the problem. Okay. So, our input consists of an array D0 through Dn. So, this is going to represent the dimensions of the matrix. Okay. So, Di minus 1 and Di respectively will give the number of rows and columns of matrix Mi. Okay. So, this means that the number of rows of matrix Mi plus 1 will be Di. So, which will be equal to the number of columns of matrix Mi, which is as it should be, because only then can we think of the product Mi times Mi plus 1. So, although we have n matrices which are being multiplied and this is supposed to represent the dimensions of n matrices, we only have n plus 1 numbers over here. Our output is supposed to be a rooted binary tree with m1 to mn as leaves, and this whole thing should give us the least time for computing the product. Let me now state again that if you give me a tree, okay, I can estimate the time required for the tree, and the algorithm here is actually fairly straightforward. So, if you give me a tree, then the time required for the left subtree can be estimated recursively, the time required for the right subtree can be estimated recursively, and then I just add up the two times, but that does not finish the total time. I have to take the product represented by the left tree, the product represented by the right tree, and I have to multiply them together. So, I need an additional term over here. So, just to clarify, suppose we consider a tree in which the left subtree has I leaves. So, say M1 through Mi belong to the left subtree, okay, and Mi plus 1 through Mn are leaves for the right subtree, and so we take the product over here. Okay. So, this has some cost, let me call it CL or CL, and let me call the cost of this CR. Okay. So, what is the cost of this entire tree? Well, so the cost is going to be CL plus CR plus computing the product, the product of these matrices with the product of these matrices. But what is the product of these matrices? What is the dimension of the product of these matrices? So, that is simply the number of rows in this matrix, which is D0, times the number of columns in this matrix. Okay. So, let me write it over here. So, this or here, this product is going to be D0 times the number of columns over here, so times Ti. This product is going to be Di times Dn. So, as a result, what we are going to get is the total time or the time to compute this last product, which is the only term remaining over here, is D0 times Di times Dn. So, stated here, the time taken is the time for the left subtree, time for the right subtree plus D0 Di Dn. Okay. So, here I was using subscripts, here I will just use array accesses, but you know that they really mean the same thing. Okay. I mean the same thing by them. So, how do we solve this problem? So, here is a simple brute force algorithm. So, we will generate all possible n leaf trees and we will calculate the cost for each. Or cost is really the same as time. In optimization literature, it is more customary to think of costs. Okay. So, I might use or I will use cost to represent time in the rest of the lecture. So, we calculate the cost of each of these trees and then we will return the one with the minimum cost. As remarked earlier, this is going to be too slow because the number of trees is going to be exponentially then. We would like to solve this problem, or we would like to see if dynamic programming can be used to design an efficient algorithm for solving this problem. So, let me give a quick overview of what dynamic programming, the whole dynamic programming idea is. So, in dynamic programming, the first step is to cast the problem as a search for an object over a certain search space. So, this certain search space we have to define a bit clearly, just to clarify our thoughts. Then we also need to define clearly an objective function which is to be minimized or maximized. In our problem, we have really done this step, okay, because the search space is simply the space of all possible trees, and the cost function is the time, and that is to be minimized, okay, the objective function or the cost function. The next step is to design an algorithm which partitions the search space, and each partition is searched to find the best element in it, or in our case the best tree in it. Now, here is the key idea: each partition is to be searched, but we can do this recursively. So, we find the best element in each partition, and since we want the best element in the entire space, we just take the best of these bests. Dynamic programming does not stop at this step too. The last and the most important step perhaps, or the most unusual step perhaps, is that we are going to characterize the recursive calls which were made over here. So, in this we will be making several recursive calls. We will ask the question, is there anything interesting about those calls? Is there any property that we can identify for those calls? Or somehow can we say that the calls are only made on these arguments? Okay. So, once we get a characterization, we are going to build a table in which the results of all these calls are going to be stored. Okay. So, we have identified which are the calls which are going to be made over the lifetime of this algorithm, and we will have an entry in this table corresponding to each such call. Then we will define a procedure which I will call fill, which will be able to fill the table entries using other table entries. The key requirement is that fill should not be recursive. Fill should not be a recursive function. If we can do this, we will have a dynamic programming algorithm, and if everything works right, this will be a fast algorithm. So, let us see how we can make this work. So, the first thing is to look at the search space. So, let us quickly take a look at that. So, the search space in our case is all possible trees with M1, M2, the matrices at the leaves. Okay. Note that we have not actually been given the matrices, and we do not need them. We are not actually going to calculate the matrix product. Okay. We are just going to design a scheme for calculating the products. So, even though I say that M1, M2, Mn are the leaves, I really mean that there are some placeholders M1, M2, Mn where the matrices can eventually be placed. So, there are these placeholders M1, M2, Mn which are going to be the leaves, and we are going to consider all possible trees, and that is going to be our space S. Our objective function is going to be a cost. We call it a cost because that is something that we want to minimize. Okay. So, our cost is going to be the time required for a tree, and we have already seen how we calculate this time. Okay. So, our goal is to find the minimum cost tree from this S. The next step is to partition this S. Now, there are several ways in which we could partition. If we have, so this is the place where we require some creativity. However, I am going to point out a very natural way of doing this partitioning. So, S is the space of all trees. I am going to define S sub I as that subspace. Okay, so that subspace in which consists of all trees in which left subtree of root has M1 through Mi at the leaves, and right subtree of root has Mi plus 1 to Mn at the leaves. So, in fact, it is going to be a tree which looks like this. So, in this picture, I have M1 through Mi at the leaves of the left subtree. So, in fact, let me call this subtree L, and let me call this R. Now, I have not told you what structure L is going to have. It could have any structure whatsoever. I haven't told you what structure R is going to have. That could also have any structure. So, all such trees which have this form are going to be in this subspace Si. So, I am going to consider a subspace for each value of I going from 1 to n minus 1, because I want at least one leaf in this side and one leaf in this side. So, if I take the union of these subspaces S1, S2 all the way till Sn minus 1, I will get my original space. So, every tree in this original space is placed somewhere in one of these subspaces. The next question is, how do I search Si? So, if we can design an algorithm for searching Si, then we'll be able to find the best in Si, and then we'll take the best of the bests, as we had said earlier. So, whenever we look for something, it is usually a good idea to characterize, to define some property of it. So, say I am looking for a tiger in a forest. Well, it would be useful if I say that a tiger has stripes, or it is yellow, or it is a large animal. Okay. So, if we can define some properties for the best tree that we are looking at. So, let us say T is the least cost tree in this Si, and if we can define some properties for it, then it will help us in actually finding T. Now, here is the main property of T that we are going to use, and it is actually a fairly natural property. So, the main lemma that we are going to prove is this. So, let L be the left subtree of T, which is a least cost tree in Si. I am saying A and not the least cost tree, because there could be several least cost trees. So, T is just a least cost tree in our subspace Si, and L is its left subtree. The interesting observation, or the interesting guess perhaps right now, is that if T is the least cost tree, then somehow we expect that L also should be a least cost tree. But L is only over the L only is computing the product M1 through Mi, and so our claim is that L must be a least cost tree for computing the product M1 through Mi. And the proof of this follows in the standard dynamic programming like argument. So, we are going to assume contrary. So, we will assume that L prime be the optimal or the best tree for this product M1 through Mi, okay, and its cost, and the cost of L is actually greater than the cost of L prime, which has to be the case if we want to claim that L is not optimal. So, L has cost strictly bigger than L prime. Okay. So, let me draw a picture over here, another picture. So, this is L, this is R, and say this is my tree T. Okay. Now, what we have just claimed is that there is a tree L prime, and this has leaves M1 through Mi, and the cost of this is smaller than the cost of this. Of course, L must also have leaves M1 through Mi, and let me write down the leaves over here as well. This should be Mi plus 1 through Mn. Okay. Here is what we are going to do. Here is sort of the standard dynamic programming idea. I am going to construct another tree T, but this time I am going to place L prime instead of L. So, my tree T prime is going to look something like this. So, I am going to have L prime over here, and I am going to retain R as it was, and I am going to connect these two together. So, this is my tree T prime. So, so T is known to be optimal. So, this T is optimal, and I do not know anything about this, but I would like to estimate the cost of this. So, let us look at the cost of T first. So, cost of T is equal to cost of L plus cost of R, okay, plus d0 di dn. So, this just comes from this observation which we had made earlier. Now, what do we know about cost of L? Cost of L is bigger than cost of L prime. So, if I substitute cost of L prime over here, I get that cost of t is bigger than cost of L prime plus cost of r plus all of this. Okay. Now, this entire expression really, if you look at this picture over here, you can see is nothing but cost of t prime. Okay. So, this entire expression is equal to cost of t prime. Okay. So, what have we proved? We have proved that cost of t is bigger than cost of t prime, or t prime has a smaller cost than t. Okay. But we had made a claim about t. So, we had claimed that t is optimal. Okay. So, t is optimal for this space S I. So, t is the best possible tree of this form, okay, with I leaves on the left side. It is the least cost tree. But we have just found that t prime has even smaller cost than that. So, we have a contradiction. Okay. So, we have a contradiction, and therefore, our basic statement must be true, that L must also be a least cost tree. Okay. So, if t is a least cost tree, then its left subtree L must also be a least cost tree. But we can apply the same argument to the right side as well. So, we can argue that the right subtree of t must also be the optimal subtree over its leaves. So, we are now ready to design a recursive algorithm. So, we will call our recursive algorithm MCM, stands for matrix chain multiplication. It will take as argument an array, the array which gives the dimensions of the matrices, and it will return the optimal tree. We do not have the leaves, the matrices themselves. So, the tree will just be the tree will just have an adequate number of leaves, and the leaves will serve as placeholders for the matrices. We are only interested in the structure of the tree anyway. So, we are not actually going to perform the matrix multiplications themselves, but we are just going to indicate the order in which the matrix multiplication should be performed. The basis for writing this algorithm is going to be the lemma that we just proved, but we need to first take care of some base cases. So, suppose our array only represents a single matrix, in which case this n would be 1, we would be given just two numbers, the number of rows and the number of columns. In this case, of course, there is no multiplication to be done, but this is the base case, and here we will return a tree, but this tree will just consist of a single vertex. Now, we are ready to generate the algorithm that we use the lemma to generate our algorithm. The basic idea is that we are going to explore each subspace S I. So, here is the code for doing that. So, I here is going to be the subspace that we are going to be exploring, and I will take values 1 to n minus 1. So, for each subspace, we will first calculate the best left subtree that must be made, that must form that must be a part of the optimal subtree, optimal tree for that. So, as per the previous lemma, the left subtree of the optimal tree for this subspace must itself be an optimal tree. So, to do that, we will recursively call MCM. But this time we only want the optimal tree over the first I leaves. So, likewise, we will only be passing the I plus 1 elements of this array. So, I plus 1 elements will define the rows and columns of the sizes of the number of rows and columns of the first I matrices, and that is what we will pass. Likewise, we will construct Ri, which will be the optimal right subtree, which will be a part of the optimal tree for Si. So, this will be done by this call MCM of di through n, and this will simply be the dimensions of the remaining n minus I matrices. C sub I is going to be the cost of this. This is going to be computed using this observation. So, it is going to be the cost of L plus the cost of R and the cost of multiplying the results together. So, this is what we have over here. So, it is going to be cost of this tree, cost of this tree that we get, and the time required or the cost required to multiply the results corresponding to these two. Note over here that I am using this this expression cost of Li, and you may think of it either as a function, but more accurately you should think of it as a field selector. So, when we return the tree itself, the tree will also contain its cost. So, we are just extracting the cost out of it. So, in fact, as we design the algorithm, we should consider that we are not only returning the tree, but we are also returning the cost of the tree. Next, we will have all these CIs, and we just want to find the minimum CI, and let us call that I for which CI is minimum, and let us call that I. Let us use I to denote that. Okay. And then we are simply going to take the corresponding tree, the corresponding left and right subtrees, and make a tree out of those and return that. So, this will typically be something like Li will be a pointer to the left subtree, Ri will be a pointer to the right subtree. So, we will construct a new node which will be the new root, and we will make the root point to Li and Ri. And since we also want to return a cost, we will attach an additional field which is Ci over here. Okay, so, this is the end of the procedure. So, this is the end of the recursive algorithm that we wanted. Now, we could work with this, but to simplify matters, we will consider an algorithm in which we only compute the costs and not the tree itself. Okay. So, the idea is going to be very similar to the previous algorithm. In fact, it is going to be simpler. So, earlier we said that if n is equal to 1, then we return a single element. Okay. In this case, we are not going to return a single element, but we are going to return its cost. So, in this case, we are going to return 0. In the previous algorithm, we had Li equal to MCM of this, but here now we are going to use MCMC. So, MCMC is the cost of the optimal tree. So, Li will now become the cost, Ri will also become the cost, and so the total cost is going to be not cost of Li, but just Li plus Ri plus whatever this was. And now we are going to find the I for which this is a minimum, and then we will return the C of I. Okay. So, we will work with this, and the rest of the dynamic programming procedure will use this. Actually, we would like to simplify, we can simplify the whole thing, and here is how we will simplify it. Okay. So, let me go back to this and let me try doing this on paper, so you can see both the things at the same time. Okay. So, the idea over here was that we are going to calculate this expression, okay, and take the minimum. So, in fact, this whole part I can replace by the following expression. So, I will just write this as return the minimum over all possible values of I, okay, of what, or say in fact, or I going from 1 to n minus 1, and what is it that we are going to take the minimum of? It is just going to be this C of I over here. So, instead of Li, I will just substitute this MCMC. So, I will write that as MCMC of D 0 through I plus MCMC of D I through n plus D of 0 times D of I times D of n. Okay. So, I have just taken this expression and I have substituted MCMC over it here and this MCMC over here, and I get this expression. So, that entire part could be represented as this. So, we are going to take this expression for all values of I and we are going to find the minimum of it, and that is what we are going to return. So, this is the resulting expression. So, if n equal to 1, again will return 0, otherwise will return this, which is what I have written over here. The final step in dynamic programming is to characterize the recursive calls. So, our recursive calls which we made were for this procedure MCMC of D0 through n, and we called D0 over I over here and DIN over here. So, MCMC was called with these arguments. So, if we look at how MCMC would progress further, you will notice that each time we are taking our original range and then we are splitting it in some way. So, here we are taking a prefix of the range, here we are taking a suffix of the range. If we take a prefix of the suffix, then we will get some range. So, not necessarily a suffix or a prefix of this, but nevertheless always some subrange of this. Okay. So, our characterization could be something like this, that MCMC is always called with a subrange djk, where jk is a subrange of 0 through n. So, our entire array was d0 through n, but we will call it with some djk. So, this allows us to define a table. Since we know what all the recursive calls are going to be, we are going to allocate one entry for each possible result. So, here is a possible result. So, djk, where 0 less than j less than k less than n. So, this result, the result of the call MCMC on this is going to be stored in table entry tjk. Our next step is to define a non-recursive procedure fill, which will be used to fill this. Okay. So, if we call fill with jk, we should get exactly what is supposed to be filled over here, or it should return MCMC of djk. So, MCMC of djk, so we need to figure out what exactly is MCMC of djk. So, let us try and execute MCMC with the arguments djk. So, for that we need to go back to the definition of MCMC. So, here is what we need to do. We want to execute the call MCMC of djk. So, here is our basic procedure MCMC. So, this is being called, the parameters over here are the entire subrange 0 through n. However, we want to call it with this subrange. So, we will assume of course that the compiler will rename and make this appear like 0 through n, but when it does that, what exactly will this return? How exactly will this execute? That is what we need to understand. So, the condition n equal to 1 over here, okay, just says whether this last index is 1 plus this first index. So, this condition really should be thought of as if the last index k is equal to j plus 1. Okay, in that case, return 0. Okay. Otherwise, it is going to return this expression. Okay. So, we are still going to return this expression, but wherever the first index 0 appears, we will just put in j, and wherever the last index n appears, we will just put in a k. So, that is exactly what we are going to, what that procedure should be doing. Okay. So, MCMC when called on djk will work something like this. So, it will return say min over I going from not 1 to n minus 1, but instead it will go from j plus 1 to k minus 1, okay, and it will compute MCMC of d of j I plus MCMC of d of I k, okay, plus instead of this we are going to have the corresponding right bounds. Okay. So, we are going to get d of instead of 0, we will get j times d of I times d of k. So, this is the value that should be returned by fill. So, here is what fill in fact does. Okay. So, fill is going to do exactly this. However, fill is not really allowed to reference MCMC, and in fact, fill does not need to reference MCMC. So, when it wants to compute MCMC of dji, fill knows that this is going to be stored in tji. So, in fact, instead of MCMC, fill is just going to return T of ji. Instead of MCMC of dik, fill is just going to return tik. And then this part is going to be the same as before, and in fact, that is what fill is going to be returning. So, this procedure fill that we have defined over here is the right procedure. It is non-recursive. Okay. It does not talk about MCMC, it does not call anyone else, but it looks at the table entries. So, this is what we needed. We wanted to have a procedure which tells us how to fill the jkth entry, assuming that other entries are full. So, this is what it is doing. Okay. So, now we are really pretty much ready to write the dynamic programming algorithm. Okay. So, what we need to do next is to characterize how fill works. Okay. So, let me write down our table first. So, our table T is going to look something like this. So, here is the first index which is I, here is the first index which is the second index which is j, okay. Or sorry, our first index is j and the second index is k, okay. So, let us now look at the first step, the first statement in fill. So, it says that fill the table must contain a 0 if k equals j plus 1. Okay. So, this is 1 1. So, this will be the entry 1 1. So, this is not of interest. So, if k is equal to j plus 1, so this entry is going to be a 0. This is where k equals j plus 1, but that is not the only entry. In fact, another entry which will be 0 because of this will be this entry, okay, this entry, and so on. Okay. So, these are simply entries above the main diagonal. Okay. So, this would be the main diagonal, and all the entries above the main diagonal will be zeros. Okay. And in fact, the whole thing is going to be defined for j less than or equal to k. So, in fact, it is only going to be defined on this side. This side is not going to be used. This side and the diagonal are not going to be used at all. Okay. Now, let us examine how does fill a particular entry jk. So, let us say this is my j over here, okay, and so this is the entry that I want to fill, and this is the index k. So, the jth row kth column, this is the entry that I want to fill. How does fill this entry? So, it considers the values of tji where j ranges from tji where I ranges from j plus 1 through k. So, these are simply table entries in this region. Okay. So, let me put them in a different color. So, these are the table entries. Okay. So, these are the table entries which are needed for updating this. So, let me put an arrow going from here to here. Okay. But it also uses table entries ik. Okay. Again, I going from j plus 1 to k minus 1. So, which are these entries? Well, these are the entries which are below over here. Okay. So, the entries above the main diagonal, but below this element are also going to be used. So, if these entries have already been defined and these entries have already been defined, then fill can fill in this table entry. So, then the entire procedure is extremely simple. Okay. What is it that we have to do? we must ensure that when it comes time to fill this entry, all these entries must already have been filled. Okay. So, that suggests a very simple order in which we can fill these entries. So, here is my table. Okay. So, here is the main diagonal. So, this diagonal I am not going to do anything with, but the entries above that I am going to mark as zeros. Okay. Then I am going to start filling entries, okay. But I should fill entries such that if I want to fill this entry, then everything on this side and everything on this side is already filled. So, next I can fill this entry maybe. So, I will put a 1 over here. After that I can fill this entry, I can fill this entry, then I can fill this entry, this entry, this entry, 7, 8, 9, 10. In general, I can, let me use another picture. I can take my matrix. So, if this is my matrix, if this is my table, I will fill the second diagonal with zeros, then I will fill the entries, the rest of the entries in this order. First I will fill these, then I will fill these, then I will fill these, then I will fill these, and so on. Okay. The point is that if I fill entries in this order, whenever it comes time to fill say an entry somewhere over here, I would already have filled these entries and these entries on which this entry depends. So, that is the key idea. So, if these entries are already filled, then we can fill these entries. So, the only thing that remains to be done now is to figure out how much time the whole thing will take. Okay. So, the total time taken is clearly equal to number of entries in the table times time to fill one entry. Okay. So, this is already telling us everything that we want to know. How many entries do I have in the table? Well, T has all this entire range jk, where jk lie between 0 and n. So, we have a two-dimensional table with n rows and n columns. We are only using half of it, but clearly the number of entries is therefore O of n squared. Okay. What about the time to fill a single entry? So, if Tji and Tik are already known, then we are going to have to compute this product and we are going to do these additions. Okay. But and this has to be done these many times. So, for every value between j plus 1 and k minus 1. This range can be as large as n, and therefore, the time to fill a single entry is going to be O of n again. So, the whole thing is going to be O of n cube. Okay. So, that really finishes the entire algorithm. Okay. So, the total time is n squared times n, which is equal to O of n cube. Now, I just want to make one more comment, and the comment is about the simplification that we did. So, we said that we are not going to compute the exact tree that we wanted, but we are just going to compute the cost of the optimal tree. So, I want to leave you with an exercise, which is how can you modify this algorithm so that you actually calculate the tree and not just the cost. So, this is the exercise. So, in fact, the idea is something like this. I am giving you a hint over here. In each table entry, store the root node of the tree along with the cost of that. Okay. The root node will contain pointers to the left and right subtrees. Okay. Now, if you go and ask the question, how do I update a single element of the table, you will have to construct the root node as well as these pointers and as well as these costs. But you will see that each filling now will still be possible in O of n time. And since the number of entries are O of n squared, the total time should still be O of n cube. So, that concludes this lecture.